Hi guys, so welcome back once more. Today we are going to do question 4 from January 2019, paper 2. This question is a combination of atomic structure as well as electrolysis. So two very important topics from section A. Define the following terms: atomic number as well as mass number. So this is going to lead back into nuclear notation. For nuclear notation in chemistry, we are given your mass number on top and the atomic number below. So your atomic number, also known as your proton number, is just going to indicate the number of protons in the nucleus of an atom. Your mass number, on the other hand, is the sum of the number of protons as well as the neutrons present inside of the nucleus of the atom. Now, inside of the nucleus, that actually accounts for the entire mass of the atom, because the mass of a proton is 1, the mass of a neutron is 1, but the mass of electrons tends to be negligible. We give 1 divided by 1840 as the fraction. If you type that into your calculator, you would see it's a very, very, very small value in comparison. So that is why your mass number is the sum of the protons and the neutrons. Remember, that is what is located inside of the nucleus. So a quick sketch of your atom. So inside of your nucleus, you have two subatomic particles, your protons and your neutrons, and around it in orbitals you tend to have your electrons. All right. Sodium is a metal with an atomic number of 11 and a mass number of 23. Draw a diagram to show the arrangement of electrons in a sodium atom. They're asking for a shell diagram. So we need to figure out our electronic configuration first. Our atomic number gives us information for the number of protons. So we have 11 protons inside of a sodium atom. This was given here by the atomic number. An atom is neutral, meaning we don't have an overall charge. So we must have the same amount of negative particles. Protons have a positive charge. Do you guys know which subatomic particle will have a negative charge? It would be electrons. So if we have 11 positive charges, how many negative charges do we need to balance this off? The answer would be 11 as well. So we actually know the number of electrons inside of this atom. It will be 11 electrons as well. So this way our positive and negative charges cancels out to give us a neutral atom. Since we have our mass number, we can calculate the number of neutrons. How can we get the number of neutrons? We have our atomic number and we also have the mass number. Your atomic number is just the number of protons. Your mass number is protons plus neutrons. So maybe we can minus them. 23 minus 11. So that will give us 12 neutrons. So our protons and neutrons are located inside of our nucleus. So just making a quick sketch. But what we really need to figure out is what is going to be in the orbitals around. We need to figure out how our electrons are going to be arranged in the different energy levels. The 11 electrons are not just going to be placed in one shell. It is actually going to go into different energy levels. There's a rule that you guys need to remember. 2, 8, 8. So in your first energy level, the one closest to the nucleus, it has a maximum capacity of 2 electrons. Your second shell can hold up to 8, and your third shell can hold up to 8. So let's see if we can place these 11 electrons. Let's figure out our electronic configuration. 2 out of the 11 will go in the first shell, right? So do you guys agree with this? We have 2 as the first part of our electronic configuration. Now we still have 9 remaining. 8 out of the 9 would go in our second shell, because that is the maximum capacity of the second shell. We have 1 remaining. That 1 will go into the third shell. So this is what we call the electronic configuration for sodium. That is giving us a lot of information. It's telling us that we have 3 occupied shells. So you are going to draw 3 circles around the nucleus. So this first circle that I'm drawing here does not count as a shell. This is our nucleus. So you guys are going to draw 3 additional circles around it, and we are going to place our electrons inside. So here I have my nucleus in a different color, just so you guys don't get confused. Inside of the nucleus, we usually put the atomic symbol, but because we had enough information to figure out the number of protons as well as the number of neutrons, instead of the symbol, we could have put the number of both of them. Either one is fine. Now in our first shell, according to our electronic configuration, we have 2 electrons. Notice how my 2 electrons are very far apart. Electrons have negative charges. Like charges repel. So these 2 electrons will not pair up because you only have 2 inside of that one shell. They will be as far apart from each other as they could possibly be. Now in our second shell, it's completely filled. You have 8. Because it's completely filled, notice that we have electrons pairing up. They only pair up when they have to. And in that last shell, we just have 1 lone electron. This is how you will get your shell diagram for sodium. State which period to which the element sodium belongs to in the periodic table. Our modern periodic table is composed of groups and periods. So your groups are the vertical columns and the periods are the horizontal rows. Now we can figure out all of this without looking at the periodic table. Your electronic configuration can help you figure out the group and the period that a certain element belongs to. So let's go back to take a look at our electronic configuration. Our period number is the number of occupied shells. So are you saying that sodium has 1, 2, 3 occupied shells? So it actually means that sodium belongs to period 3. And feel free to double check this with an actual periodic table. You would see that sodium is located in the 3rd horizontal row. We can also get the group number from our electronic configuration as well. Your group number is the number of valence electrons. Valence just means outermost. So it's the number of electrons in the outermost shell. So this would be called our valence shell. So because we just have 1 electron inside of that shell, it means that sodium belongs to group 1. So if you look at a periodic table, you would see that sodium is in the 1st vertical column and the 3rd horizontal row. We got this from our electronic configuration. One more thing I want to mention, notice how when I wrote the period number, I used whole numbers 1, 2, 3. But for group numbers, we use Roman numerals, all right? So there are different ways for you to write those answers. They're just asking us for the period number. The answer is period 3 because we have 3 occupied shells in a sodium atom. Describe the type of bonding in a sodium metal. There are 3 types of chemical bonds: ionic bonds, covalent bonds, and metallic bonds. Just a quick recap, ionic is between a metal and a non-metal. We find metals on the left-hand side of our periodic table, non-metals on the right-hand side. For covalent, it's where we have 2 or more non-metals bonding. And metallic bonding is just what is happening inside of a metal itself. So which one do you think is going to be the answer here? We need to describe it, but first, we just want the bonding inside sodium metal. So it means we are going to be dealing with metallic bonding. We need to explain what is happening. Now I want you guys to remember the arrangement of particles inside of a solid. Metals tend to be solids at room temperature, with the exception of mercury, which is a liquid. So we have our particles tightly packed together in a regular repeating arrangement called a lattice. So I'm going to make a little sketch here for you guys. So these are our sodium atoms tightly packed together. But what tends to happen inside of our metal structure, our valence electrons tend to become delocalized. So remember we just drew the shell diagram for sodium. That last electron in the third shell tends to become detached. So it's no longer attached to a particular atom. It's now free to move about. So we have our electrons free to move about now. And because that electron has detached, our atom is no longer neutral. It develops an overall charge. So we tend to get a positive charge remaining, and we have negative charges around it. Whenever you have opposite charges, you have very strong electrostatic forces between these charges, and this actually holds your metal compound together. Because these forces of attraction are so strong, that is why metals tend to have a very high melting point as well as boiling point. Metallic bonding occurs within the sodium metal. The metal atoms are packed tightly together in rows to form a metal lattice. So a lattice is where we have a regular repeating arrangement. The valence or the outermost electrons becomes delocalized. So delocalized means it becomes detached from the atom and free to move about. So because of this, we now have the formation of ions, which have a positive charge and the negative electrons. The lattice is held together by the electrostatic forces of the attraction between the electrons and the cations. So this is how you can describe the bonding inside of sodium metal and all metallic bonding in general. So that's it for this video, guys. We just have a little piece on electrolysis to do next, and that will be it for this paper.